Okay. So, do you guys have any questions or anything that came up um, that we can look at or you want to chat about before we jump into today's stuff? I saw that a good portion, I think the roster now is like 17, and I think about 14 are on My Open Math, so that's good. So, good.
I'd like to complain just to get it off my chest.
Okay, what's that?
Somebody's got to hear me complain. No, just a challenge with the bookstore. I'm just having a challenge with the bookstore.
Okay, what's going on?
I guess I'm a little bit old school and trying to get them to call me rather than do a lot of emailing. Been a little bit trying for me, but it's working out. I'll hopefully have some books next week or in 2 or 3 days.
Well, I'm glad we've got the copies of those first couple chapters. That should help.
I appreciate that.
And I know they're in the middle of transitioning from their more in-place bookstore to the online bookstore, so that transition might have a little bit of extra trouble to it. Summer is often a time where they try to put in changes because it affects as few people as possible, but it does make for challenging.
I'm good now that I have complained.
Good. Sometimes that just helps, just having, out there. Hopefully,
good to move forward.
Hopefully, you guys aren't having too much trouble with the registration issues. But if something does come up with that you guys need, let me know. The best thing to do is just make sure you're signed up on My Open Math. As long as that's happening, I can fix everything else with the school. Okay. So yesterday we talked about data types a little bit. And our big data types essentially broke into 3 groups. We had our categorical data, and our quantitative data. It's being weird. And that quantitative data broke into discrete. My brain just turned off. Discrete and continuous. Hopefully you had some chance. That's not how you spell continuous. Trust me, that says continuous. Hopefully you guys had some chance to look some of that over and start working on some of the online stuff for those data types in chapter 1. What I want to look at today is starting to look at different ways that we will use to organize data and some of our kind of data display types. Because let's say, for sake of argument, you were collecting data on something, let's say categorical, and we were trying to look at colors of, boy, the classic is M&Ms, but let's say coins. Let's say you had a big pile of coins and you were trying to make a list or organize your data on what type of coins you have. So, you might have some dimes, you might have some nickels and pennies and quarters, and, these might just be in some big pile of coins that you've got to figure out what you've got and want to organize this into some nice and useful organization of data. Oftentimes when we get data in practical applications, it is fairly chaotically arranged. So, if you had this, nice big pile of data, and somebody asks, what do how many pennies you have, or how much money is here, it would be kind of an irritating way to look at a big pile of data. Just having this, you know, all the data is there. It's just not in a very useful format. So what I want to look at today are some different tools that we have that we're going to use for organizing this kind of data nicely. It might be handy for you guys to have calculators around for this. I've got one here, but it is nice to just be able to ask you guys what certain values are. So having that at your disposal will be handy. I'll bring mine up anyway, just in case I need it. So one of the most common, oh, I don't have that calculator anymore. I will need your guys' help for calculators today. So one of the tools that we will use a lot for both categorical and quantitative data are frequency tables. So we're going to start with those. So frequency tables. Since we are going to be looking in this course at one of variable data, we're not going to have to worry about like trying to graph one data type versus another data type for the most part. What we're going to have is a data type on our horizontal, and on our vertical, we're pretty much always going to be worried about frequency, how often that particular data type comes up. So frequency tables are going to be a really common tool for us to organize that into. So when we build a frequency table, it's nice for us to determine what kind of data we have. So this pile of coins here, is that pile of coins categorical data? Is it quantitative data? If it's quantitative, is it discrete or is it continuous? What do you think? Kim's saying discrete. So that means, Kim, you're saying quantitative discrete?
Yep. But I was just trying to show you the spelling. You got the E and the I backwards.
Oh, I did. That was weird.
Not that it's a big deal, but I still think it's discrete.
Still think it's you're going to stick by the thing you said a while ago for something else? Anybody want to argue with that? Of course, it's an I. Silly. So why discrete, Kim?
You can count them.
We can count how many there are, but our actual data isn't our frequency. Our actual data is the existence of a dime, a quarter, a nickel, or a penny. So if we're asking essentially, what is this coin? That coin is a dime.
Right.
As opposed to this coin that is a nickel. Is the label of a nickel and a dime a category or a value?
A category.
A category. Now this is going to be, that distinction is going to be really important because it's very common as we look at frequencies to look at that frequency value and think of that as our data.
Mm-hmm.
That frequency is how often our data occurred. Our data is what type of coin is this. Fair? So we've got here categories, and if you were going to make a table, our table would probably look like pennies, dimes, nickels, and what, quarters. Those are categories, right? Well, that makes it essentially categorical data. But what you're saying, Kim, you're probably just saying these things to give me nice things to complain about. But
Doesn't that make it qualitative then?
the frequency is, yes, it makes it qualitative. Or categorical is another word for qualitative.
Yeah.
I'll tend to use categorical just because qualitative and quantitative are easy to switch. So if we wanted to organize this into a frequency table, all we would need to figure out is, well, how many of each of these things we have. So we can count them up. How many pennies do we have in our pile of coins? 1, 2, 3, 4, 5, 6. Is that 7? Did I miss any? Looks like 7. Okay, and dimes. How many dimes we have? We've got 1, 2, 3, 4, 5, 6, 7, 8 dimes. Did I miss any dimes? Oh, that's good. What's 8 dimes? Nickels. I don't know what color I should use for nickels. About pink. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nickels. Looks like all my nickels. And our quarters, 1, 2, 3, 4, 5, 6, 7 quarters. Looks like all. So, frequency table. Instead of having to look at this, excuse me, big pile of coins or big list of its numerical data, a big list of numerical data, or whatever chaotic form our data comes to us in, we can have this frequency table that represents all of those data. Instead of having to have 7 pennies and 10 nickels sitting there to look at, we could look at a nice compact frequency table. Nice thing about frequency table, if somebody asks us how many coins we have here, as soon as we have a complete frequency table, we can answer questions like how many do we have without having to go back and count in that big pile. If we wanted to find out what the total number of coins we have are, or the total number of data points we have, what could we do with our frequency table?
Just add up the frequencies?
Yeah, the sum of the frequencies. See, 18 plus 14, is that 32? So we want a little total. We had a nice little sum. So we had 32 coins. 7 of them were pennies, 10 of them were liquors, 7 quarters, and 8 dimes. That's a nice organization of our data. Is that fairly straightforward? Not having any crazy talk yet. If we wanted to make it a little bit more, have a little bit more fun with it, we could change our frequency table into a relative frequency table. And we will use relative frequency tables fairly often. So it's good for us to know what those are. So, relative frequency table will still have our categories. So we'll still have our pennies, our dimes, our nickels, and all our quarters. But instead of having frequency in that other column, we will have relative frequency. Relative frequency essentially tells us, instead of how many do we have, it tells us what proportion we have. So instead of having 7 pennies, we say we have 7 out of 32 pennies. So this would be 7 of the 32. Now, we could list it as fractions, who doesn't like fractions, right?
Yep.
But often we'll see relative frequency listed as decimal proportions or even percentages. I think I'm going to stick mostly for us with proportions because we'll need to be thinking in proportions for some of the things we're going to do later. So we'll stay in the kind of decimal proportion as opposed to moving that decimal point over to have it in percentages. So if somebody has a calculator out there, can you tell me what 7/32 is? As a nice
0.22,
thing.
22 hundredths rounded.
So 0.22?
Yeah.
Okay. So that gives its proportion. We could call it 22% if somebody wanted to, or 22 100ths. You know, it's a nice proportion of 0.22. That is the relative frequency of the pennies. What about the dimes? Well, we have 8 dimes out of 32 total. So
Is a fourth.
8/32 is a fourth, yeah, so 0.25.
0.25.
The quarters, I'm going to skip over the nickels and go to the quarters because the quarters are 7 again, and we already know what 7/32 is, right? 7/32 is 0.22.
Right.
So even if we didn't know, say for example, we didn't know how many nickels we had, could we figure out what the relative frequency of the nickels should be?
Total needs to be 1.
Yeah, all the proportions, all the relative frequencies added together should be 1 for 100%. So we could add those together and subtract from 1 to find that relative frequency. Or we could take the 10 divided by 32 and do it that way. What is the 10 divided by 32?
0.31.
0.31. That seem nice and reasonable? So sometimes frequency is preferred. We want to know how many we actually have. Sometimes relative frequency is more useful. We don't care so much about how much we have as we care about what ratio or what proportion we have. Depends on what we're doing. The nice thing about relative frequency tables is we always know what their total will end up being. Their total should always be 1. Now you got to be a little careful about that. Sometimes if you're, when you're rounding things off, like depending on how these numbers rounded or how you rounded them, this total might not be exactly 1. It might look like, 0.997 or something trying to approximate 1 because you've done some rounding. That is the nice thing about having the fractions instead. If you had 7/32, 8/32, 10/32, and 7/32, it would always add up to a perfect 32/32. But when you do some rounding, sometimes this 1 is affected by that rounding. But effectively, it should always add up to that 1. Questions about that? Okay. So some of the ways that we can build other displays of data from this, oftentimes, even if we're using other data display types, we will often build frequency tables first, just because frequency tables are really handy. But going from a frequency table, it's fairly easy to make things like a bar graph or things like pie charts. One of the things that we will do on our lab on Thursday is learn how to make bar graphs and pie charts nicely in Excel. Excel has some very, very nice tools for making pie charts and bar graphs very quickly and fairly easily once we learn how. So we'll practice that some on Thursday. But we can make bar graphs by hand. So if we want to make a bar graph, we'll have our categories along the bottom. So the pennies, the dimes, the nickels, and the quarters. And again, along the vertical should always be our frequency. So, for example, the pennies were a frequency of 7. The dimes had a frequency of 8, so a little bit higher. The nickels had a frequency of 10, so even higher. And the quarters went back to a frequency of 7, so it should be the same height as the pennies. So a nice little bar graph. We should have the scale here nice and labeled. Always make sure you've got labeled scales. The colors don't have to match. I'm just making the colors match for my own amusement. Our axes should be labeled with our categories along the bottom, should say frequency along that vertical. And technically, anytime you make a graph like this, you should always have a label. So I'm going to just label it coin types. And we have a nice bar graph for our frequency table. Now, if we wanted to, instead of doing frequency, we could do a bar graph in terms of relative frequency. Instead of using the 7, 8, 10, we could use those proportions. So the pennies and the quarters would both be a relative frequency of 0.22. The dimes would have a relative frequency of 0.25. And the nickels would have a relative frequency of the 0.31. So we'll see bar graphs based on frequency sometimes. We'll see bar graphs based on relative frequency sometimes. Both are perfectly fine, perfectly useful. Cool. Similarly, pie charts. I'm assuming bar graphs and pie charts are something you've all have seen and played with out there in the world. So pie chart, we usually make them circular, though not always out there in the world, but I'm going to presume our pies are circular. And we break that into wedges, or technically sectors, for each of our categories. It is not always done, but it is important to make sure that when you make a pie chart, we're going to be breaking these into these 4 pieces. It is important that the amount of angle in each of these wedges is correct to the actual proportions in our relative frequency. So if you were trying to draw a pie chart out nicely, we know that there are 360 degrees in a circle. So this arc here should be, if we did the dimes, it should be 25% of that 360. So that should make this arc 90 degrees. The arcs for the pennies and the quarters should be 22% of this. So whatever 22% of 360 is, should be the angle in both of those sectors. And similarly, 31% of the 360 should be that angle. It is not uncommon for people to draw pie charts where those wedges are not in the correct proportions. Sometimes it happens just because people are being kind of fast and trying to make a quick chart, not being careful. But it's also sometimes done to mislead people. You can make something look more or less important or more or less significant than it actually is by manipulating those angles and fooling your audience. So a honestly done pie chart, those angles should be precise, relatively precise. So, using something like a compass and a protractor or whatnot to get those angles right is nice. But also the nice thing about things like the Excel tools that we will use to make pie charts is those Excel tools automatically make those angles correct in their proportions. So we won't have to fight with doing that. We won't have to calculate those angles because Excel will handle that for us, which is nice. But again, we want a title for coin types. And we want to label each of our pieces. So what this was dimes, pennies, quarters, and nickels. I think that quarters one needs to be a little bit bigger and the nickels a little bit smaller. But again, I didn't have a protractor and so I'm trying to guess here. And we should label them by value. Sometimes the labels will be in the pie chart. Sometimes there's a little key off to the side. But we could label these either with the frequency or with the relative frequency. You often see, oops, shouldn't mix them though. You often see pie charts in terms of their relative frequency, because in pie charts, you're often worried about those proportions. But sometimes it's actually kind of nice to have the frequency represented by the label, by labeling your frequency, and the relative frequency is kind of visually represented by the size of those sectors. So in some ways, you can kind of get, two pieces of information in there at the same time by visualizing the proportion with the size of the sector and having the actual value so you know how many you actually have. So you can have some fun with pie charts in that way. But again, we'll practice doing some of that with some of our tools in Excel. Again, I presume you guys have seen pie charts and bar graphs throughout your careers. Any questions about any of those before we kind of look at some more quantitative tools? Okay. How do I want to do it? Now, I don't want to give you the impression that frequency tables are fixed to categorical data. If we had, instead of these, nickels, dimes, quarters, and pennies, if we instead gave the nickels, dimes, quarters, and pennies their numerical values and looked at the pennies as 1 cent, the nickels as 5 cents, the dimes as 10 cents, and the quarters as 25 cents, we could still make a discrete value table. Now, it would be discrete because we're talking about US coins here. So there is no coin between 1 cent and 5 cents. Fair? There's no 4.5 cent coin. So value-wise, it would be discrete. Nothing between 5 and 10, nothing between 10 and 25. And we'd have the same numbers. Got to be careful where they are because I changed things here. There were 7 1 cent values, 10 5 cent values, 8 10 cent values, and 7 25 cent values. This is still frequency, but here this is value. And we've got a discrete quantitative frequency table. Fair? And we can make a bar graph out of it. We can make a pie chart out of it. Discrete, especially discrete quantitative frequency tables can be tough to read because this is just a big array of numbers. It can start to get kind of confusing about which numbers are your values and which numbers are your frequency. Fair? So for example, again, if we asked how many coins we have, we'd be adding up these numbers to figure out how many coins we have. We still have 32 coins. But if we wanted to figure out how much money we have, would we add these values together? What would we have to do to figure out how much money we had?
Multiply the value of the coin by the frequency and then add those.
Yeah, we'd have to multiply these together and then add those results together. So you really want to get used to when you're looking at frequency tables, even though we don't want to have to write out the data, this frequency table does say we've got 7 ones. I just don't want to have to write out 7 ones. And it says we've got 10 fives. I said I didn't want to write out 10 fives, but here I am. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 8 tens. You guys don't want to have to write that out, do you? 2, 3, 4, 5, 6, 7. I know you don't. We don't want to write that out. The frequency table is supposed to help us see that without having to have all that data written out. Because even writing these out, okay, it might be nice to write them out, but you keep having to count up how many there are. We don't want to do that. But we have to recognize when we look at a frequency table like this, that that 7 is a how many we have and not one of our actual values. So do be careful about that, particularly when we start doing things like trying to find totals and averages and whatnot. It can take a little bit of getting used to. And we'll see that when we start finding particularly averages based on frequency tables. So we can use frequency tables for discrete data, just like we can for categorical data. For continuous data, though, we do have some issues. So let's focus here for a minute on continuous data. Now, I can't really use my pennies and nickels and dimes for continuous data because it's not continuous information. So let's say instead we had a bunch of pennies. I don't know why coins today, but why not? So let's say we had 50 pennies. How you spell pennies, right? Spell pennies? Like no.
2 ends.
2 ends?
Yeah.
Pennies? Pennies? It does look better. So you had 50 pennies. And you wanted to weigh those 50 pennies. 50 pennies, find weight. You thought I'd get the whole IE thing wrong, didn't you? 50 pennies and you wanted to find their weight. And we wanted to organize that into a nice table. Well, the first thing we would need is 50 pennies on a scale. I think I've got 50 pennies on a scale here somewhere, but I don't want to actually do that because of the time that would take. But the problem is, if we weighed all 50 pennies, we would get 50 different weights. It is impossible to have 2 pennies that weigh exactly the same amount. Now that might bother you a little bit. It's like, you know, it's the idea that it's impossible to have, say, two people that weigh the same amount. Well, you can find two people that weigh 170 pounds. But do those two people weigh exactly the same? Not if we allow that weight to be continuously distributed. That person might be 170.2138734,972 pounds. Well, the other person is 170 and something different in the decimals weight. Fair? If you go far enough down those decimals, you will eventually find a difference, however slight, in their weight, right? So what do we tend to do? Instead of having everyone listed as entirely different weights, we round them off to the pound, right? We essentially make a category for any particular pound range. We say anybody who's between, say, 169.5 and 170.5, we put in one bin for 170 pounds. Fair? So we would do the same things with our pennies. We probably weigh them in grams. And instead of having their exact grams, we would have a range of values. Now, this would be nicer if I kind of had an idea of how much a penny weighs in grams. Anybody know off the top of their head how much a penny weighs in grams? If only we had, say, the internet. Pennies in grams. 3.11 grams plus or minus 1.3 grams. Cool, that's enough for us to kind of make up anyway an array here. Oh, the copper-plated zinc pennies weigh a little less. Okay, so let's say we're weighing a bunch of, and you know, they're all going to be different weights. So let's say, you know, if anything between 2.01 grams to 2.2 grams, we put in that category. Anything from 2.2 to 2.3, anything from 2.3 to 2.4, 2.4 to 2.5, 2.5 to 2.6, and anything from 2.6 to 2.7, we'll put in that category. Now, this might seem a little strange. If you get a penny and we weigh it, and this particular penny is 2.2 grams exactly, which again is physically impossible, but up to our rounding, it's exactly 2.2. Does it go in this first block or this second block?
Wouldn't it depend on the next number?
What's that?
Would it depend on the next number, like the 2.2, if it's higher or low after?
It would, assuming though that this was 2.200000000 forever. If there was anything after that 2, you're absolutely right. It would definitely go in the second one. And again, we know it's technically physically impossible for it to be exactly 2.2. The probability of that is exceedingly low. But let's say it's 2.2 exactly up to our ability to measure. All of these categories are technically from A to B. You guys remember our notation for intervals? The square bracket means include that point. The parenthesis means don't include that point. So these categories, it starts at 2.1, including 2.1, go up to, but not including 2.2. The 2.2 is included in the second set. and then up to, but not including 2.3. Fair? So let's say that we then had, of our 50 pennies, we had, I don't know, say 5 in that range, 4 in that range, 8 in that range, 11 in that range, 9 in that range. Could we figure out how many has to be in that range? Andrew, however would we do that?
Subtract all those values from 50 and see what's left.
Yeah. All of these frequencies have to add up to our total number of data values, which is our 50. So that sum has to equal that 50. So what do we got? We got 20 plus 12 plus, so 20, 17's 37, so 13. Is that right? I did that way too fast. Is that right?
Yeah, that's what I got.
Cool. So to force those to add up to 50. Could we put this, instead of in frequency, could we put this into relative frequency? Well, under the presumption that you're all saying, yes, of course, we could turn that into relative frequency. Take a moment and do that. I'll give you one of them. How about just, I can do that one. So take a moment and turn all those into relative frequencies. So what should they be? 0.08, 6, 0.26, 0.18. Is that what you guys got? Cool. And again, in another day or two, we'll look at Excel. Nice thing about Excel is Excel can do a lot of these calculations for us very, very quickly. So if you have had some experience using Excel, you'll be perfectly fine, perfectly happy. If you don't have any experience whatsoever doing Excel, we do kind of go through an introduction of using it. I do recommend before Thursday, though, making sure you've got nice access to it, either through Microsoft Open Office or through getting yourself the Microsoft Suite from from the school, like we talked about yesterday. And looking at it a little bit, maybe if you've never used it before, maybe go onto on YouTube and look at some tutorials. Getting some familiarity with it ahead of time would be handy, just so it's not overly terrifying. But we don't do anything horribly complicated with Excel, but we do want to take advantage of some of its power. Fair? So given this either relative frequency table or frequency table, sometimes we put them both together, nice. For continuous data over these intervals, these intervals will often refer to as bins when we're talking in terms of, making histograms out of them. So you might get used to the idea of calling those bins. But when we make a bar graph out of this, we actually get a particular type of bar graph. So that bar graph, if we've got from the 2.1 all the way to the 2.7, we know our data isn't in discrete chunks between these two. We know our data is moving smoothly between them, because we know that these bins, these chunks that we've broken it into, are kind of a false creation of ours, right? So often when we make a bar graph out of continuous data like this, instead of making it in these, kind of big separate bars like we did over here, we'll kind of take these bars and jam them all together to kind of visually represent that this is really one big set of intervals. So between the 2.1 and the 2.2, we had, 5? So we've got those 5 in that first bin. And then 2.2 to 2.3 was 4. 2.3 to 2.4 was 8. And again, notice I'm putting these bars kind of right up against each other to kind of show that this is really is a representation of a smooth movement between one and the other. Well, the 2.4 to 2.5 was up at 13. So it's up there. 2.5 to 2.6 was 11. And 2.6 to 2.7. These intervals should really be the same length. That's just because of how I drew it. So I'm going to move that 2.7 there. 2.8. And so that was a 9. So this is our weight in grams. This is our frequency. And this is our histogram of coins. I'm going to say coin weight. Just to give it a title. Should have a title, our axes labeled and scaled. So a histogram, we'll talk about histograms a lot. Histogram really is just a bar graph, but it's a bar graph versus a frequency or relative of frequency, where your data has been broken up into bins, generally displayed in this kind of pushed together format to essentially mimic the idea that our data is really kind of doing this. Fair? We've broken it up into these kind of artificial bins. It's almost kind of like, when you're drawing something in low resolution, it gets pixelated. So instead of being smooth, it has those blocks because it's because you only have so much resolution. These bins are essentially our resolution. So if we took that off and looked at, okay, instead of it being that pixelated curve, it's a smooth curve. That smooth curve that we imagine in there would kind of look like that pink curve. Now you'll get a chance to read more about histograms and skew in your section, and we'll talk about some of those things as we go along. Let's see. Questions about any of that so far? I'm so used to 50-minute classes that after 50 minutes, my brain kind of just naturally goes, you should be summing up, Matt. No, we got another little while. So you'll get some chance to practice all of this, and that'll be good. There are a couple other display types for data that I want to look at. They're a little bit less common. Bar graphs and pie charts are, of course, you'll see those everywhere. Histograms, you'll see a lot, and we will use a tremendous amount, especially in statistics. Histograms are kind of, ubiquitous. We see them everywhere in stats. There are some less common data display types that we want to make sure that you've seen and are able to read and use. So I do want to look at those. So let's just jump in and look at those. So actually both of these are really good for discrete data. But let's look at them. First one I want to look at is a stem and leaf plot. Stem, that's steam. Is stem just S-T-E-M? That looks weird. I can usually figure it out. So a stem and leaf plot. Stem and leaf plots are really handy because they can be really fast, fast to read and really fast to write out, and very kind of well contained, but they are a little bit weird to read. So what I'm going to do here is just draw out a stem and leaf plot, show you what it looks like, and then talk about what it says. So a stem and leaf plot has two parts. It has our stem and our leaves. Those stems might just be things like, 2, 3, 4, I'm going to skip 5, say 6. So our stem are usually single digits. We could have like an 11 down here or a 12 down here. And the leaves are single digits, but the leaves end up being things like, say 0, 0, 1, 4. Nope, I should put them in order. 4, 5, 7, 8, 0, 1, 2, 2, 3, 5, 7, 1, 0, 1, 4, 8, 0, 1, 3, 5, 9, 7, 2. They don't all have to have zeros. I'm not going to take out that 0 just so it doesn't look like they all have zeros. So that's what a stem and leaf plot would look like if you just came across one. The hard part is, what is that actually saying? What are the data points that this stem and leaf plot is trying to display to us? The nice thing is, once you get used to reading them, they're actually pretty handy. The stems essentially tell us, in this format anyway, they tell us the tens place for our numbers. The leaves are all the ones places. So this stem under 2 here, that 2 is really a 20. And these values are the ones places after that 20. So our data would look like 20, 20, 21, 24, 25, 27, and 28. Just instead of having to write all of those twos, we can just tell you, okay, I've got a stem of 20s and my leaves are the 0, 0, 1, 4, 5, 7, and 8. On the stem of the 3, that 3, it's a tens place, so really that's a 30. So what are our values after that? Well, 30, a 3 and a 0, a 3 and a 1, a 3 and a 2, a 3 and another 2, a 3 and a 3, a 3 and a 5, a 3 and a 7. So a 3 and a 0, a 3 and a 1, a 3 and a 2, oops, a 3 and a 2, 3 and a 2, a 3 and a 3, 35 and 37. Does that seem reasonable? Then 40s. Okay, we do again have a 0, so we do have an actual 40. And then a 41, a 44, and a 48. Nothing, nothing in the 50s. But if we had a 5, say there was a 5 written there, and nothing here, we'd go, oh, okay, 5, but there's no leaves for the 5, so there'd be no data. Sometimes you'll see that, and that's fine. Then we go to the 60s. There is no actual 60 because there's no leaf for a 0. Our smallest 60 is 61, but 61, 61, 63, 65, 69, 60. Ooh, I put those out of order. That's weird. It's okay. They don't have to be in order. It's just polite if they're in order. So 69, 67, and 62. So you may not have seen stem and leaf plots before. They're not terribly, terribly common, but it is quite handy to be able to write all of this data in this very condensed little form. Depending on what you're doing. One of the places where, you know, I haven't used stem and leaf plots in what I've done a lot, but the couple places I have used it have been when trying to collect lots of data very quickly. So let's say we were going to collect some data. We knew it was going to be, let me do it this way. We knew it was going to be, you know, somewhere in the fairly low numbers. So we didn't expect to have numbers any more than 30. We put 40 in there just in case. And we were going to have to collect data fairly quickly. So people were going to kind of yell out data. Leaves out of 6, out of order. Yeah, out of order is okay. And they'll be really out of order here. So oftentimes, you know, when you're collecting data, if it's happening very quickly and people are just kind of shouting data at you, stem and leaf plots are really handy. If somebody calls out, you know, 9, 6, 21, 33, 18, 42, 7, 24, 34, 19, 27, 41, you can really quickly jot down that data in a very organized fashion. Fair? So, you know, and again, here they're not not in order because it's just however the data is coming in. It would be nice for us to organize that data later and put it in order because it's handy. But we can collect lots of data this way. So let's say we get more data and there's a 25, a 24, a 23, a 21, 14, a 31, a 20. 25, and I start running out of space here. Well, technically I could go as far as I wanted to, right? But oftentimes that can get cumbersome or starts getting off your page. When you're using it to collect data, notice I left kind of space in here, right? You can go down and go, okay, I got more 2s. So sometimes you'll see that happen. And so I also have, say, 23, 20, 29, 24. This data ended up being a lot of data in those 20s, 30, 19, 20, 24. It can be a really handy tool for collecting data very quickly. It is nice to then take that and reorganize it into a more proper stem and leaf plot by keeping everything in order. Now, I still don't want to have those 2s be too terribly long, so I'm still going to have 2 rows of 20s. But the kind of convention would be to put numbers that were less than 5 on the first one and numbers that were greater than or equal to 5 in the second one. So they're kind of broken up. So to put them in order, we might then go to the 6, 7, 9. Under the 1 would be 4, 8, 9, 9. And then the 20 is going to take a little while. We got 20, 0, 0. And then 2 1s. I don't see any 2s, couple of 3s. 1, 2, 3, 4 4s. And then everything else is going to go on the bottom one. So 1, 2, 5s. And I don't see any 6s. So it's just the 7 and the 9. Oh, and I missed a 0. If you're collecting data for something important, you might take a little more time than I did here. Be a little more careful. And then again, 0, 1, 3, 4, 5, and then 1, 2, to have them nicely in order. And really the ordering there is just to be polite and to make it as useful as possible. And in practice, though, what you would do generally is you would take the data here and put it into something like Excel or some other program, and then just tell it to order it, and it'll do it for you. Or you might take this data, and instead of making a better stem and leaf plot, you might take that data and turn it into a frequency table or something. So stem and leaf plots are often not how the data is originally given or how the data is eventually used or presented. It's kind of a nice in-between tool. Some people use them a lot. Some people don't like them at all, and that's all fine and good. It is fairly important for us to know how to read them, though. So just in case somebody hands you data ever in a stem and leaf plot, knowing how to read this and how to turn this, compact form into what is my actual data is really helpful. Particularly if we wanted to do something like add these all up or find an average or a total. The idea that we're adding, 6, 7, 9, 14, 18, 19, 19, 20, 20, 20, 21, 22, sorry, no 22s, 23, 23, 24. The fact that those are the numbers we have listed for figuring out what our sum is helpful. So, stem and leaf plots, fairly handy. Let's say we want to make a frequency table out of this data. We don't know what this data represents. It's just right now abstract data, and that's okay. Now, we could make a frequency table in terms of individual data and like asking how many sixes we have, how many sevens, how many nines. But most of this data we only have once or twice. A couple of things we have 3 times or 4 times. But depending on what this data is, it might be better to use bins instead. Even though this looks like discrete data, we can still build it more like a histogram and build those nice little bins. So we might want data between, say, 0 and, we might go from 0 to, I'm gonna go from 10, this is 0 to 10, and 10 to 20, and 20 to 30. Make it easy for us, 30 to 40. We could have fairly small bins, or sorry, those are fairly big bins, a fairly small number of them. But really, it's probably nicer for us to have slightly smaller bins than that. How many bins should we have? When we're making a histogram, you really want that histogram to have at least 6 bins. Anything less than 6, it's really good to differentiate more if you can. So 6 would kind of be a nice minimum. Generally, we don't want to have too many bins. Like we could make our bins length 2, say, and have, what, 20-something bins. That's a lot of bins. So usually I shoot for somewhere between 6 or 8 up to 12 to 15 on the high end. But how many bins you have for your particular histograms, it's really up to you. It's your histogram, right? I will get grumpy with you if your histogram has less than 6 bins. But sometimes that's kind of what the data is saying to you. You're like, you kind of want it to be 6 categories or 4 categories, in which case, okay, let somebody be grumpy with you. That's all right. But let's say, well, I'm going to ask you guys, how long do we want to make each of our bins?
Maybe 5s.
Maybe 5s? 5s would seem reasonable. 5s are really easy to count, right? There's 5, 10, 15, 20. If you have bin size 4, it's a little bit harder to count. Or size like 7 bins are always fun. But we could do 5s. And particularly since our smallest data point is this, oops, that's not what I wanted to do. I'm still on my eraser. Since our smallest data point is this 6, we could say I want the minimum value to be 6. And then you said go by 5s, so 6, 11, 16, that's a little harder to count. But it doesn't necessarily have to be that smallest value. Kind of the rule of thumb is the most convenient value smaller than or equal to your smallest point. So if we're going to go by 5s, I don't want to start at 6. Where do you want to start?
5.
How about we start at 5? Fair? This is our histogram. We can start where we want. So make that bin from 5 to 10. Then our next bin would very naturally be our 10 to 15, 15 to 20, our 20 to 25, our 25 to 30, our 30 to 35, and our 35 to 40. Oh no, I've run out of spaces. Do I need another block for 40 to 45? Does it sound like the way I said that, I want the answer to be no, I don't need it? We frankly don't. The last bin on any histogram is technically from the low point up, even if it does have an endpoint, it's really the last bin is everything that's in that bin and above. So even if it says go to 40, it's 40 plus. Because sometimes you'll have data that, I don't know what data we're collecting here, but we might have also, somebody came up and said 75. I don't want to have like 30 blank bins in there, right? That 75 is just going to go into this last one. You know, so it's not uncommon for histograms to seem to be missing, you know, some of those upper bins. Everything upper falls into the bin. Now, if you end up having a lot of stuff in this last bin, which happens sometimes, that does tell you, well, maybe I want to reorganize my bins. Maybe I didn't make, you know, the best choices in there. But it really is a set of choices. So how many things do we have between 5 and 10?
3.
How many things between 10 and 15?
1.
Was not the most confident sounding one I've ever heard, but yes, 1. Try to fill out the rest of that frequency table. Let's see, Kim, what'd you say? 313, 11.4, 4 and 3. I know I had to pick on you. So this is where that issue of like, where does the 20 go comes up, right? Does the 20 go here or does the 20 go here? As we said up above, these bins are including the beginning, not including the end. So this is starting at 15, going up to but not including 20. So the 20 should be down there. It's even a little bit tougher with this 5 especially. The fact that that 5, you know, the 30, 1, 2, 3, 4, there's 4 between 30 and 35, and that 5 goes into the 35 to 40 range. Those are, I think, some of the tougher pieces to pull out of there. Now, just for clarification, why don't we say then 15 to 19? Why don't we do that instead of 15 to 20?
Then there'd be a break in between 19 and 20.
Yeah, then where does 19.5 go? Okay, go up to 19.9. Okay, where's 19.91 go to? Right? We could play this game forever. But what about 19.9 forever? And 9's forever. What is 19.9's for forever equal to? Equal to 20. So, yeah, we can't put 19. We got to put 20. And there is a fun argument for the why is 0.9 forever equal to 1. We could have that discussion later if you wanted to. It's a fun discussion, actually. Okay. Then if we could, of course, make it into a nice histogram from there. We'd have our bin that goes from 5 to 10, our bin from 10 to 15, from 15 to 20, from 20 to 25, from 25 to 30, from 30 to 35, and from 35 to 40. And again, that one that goes 35 to 40 is 40 plus. So sometimes that last bin you'll see is a little bit high. That happens. So, and then we need a scale here. It goes up to, I'm going to put it up to 12. So 6, 3, 9. And that's our frequencies. We could turn this into relative frequency if we wanted to. I don't know what these numbers stand for. So our labels and titles are a little boring because it's just raw data. But our 5 to 10 bin is going to go up to our 3. Our 10 to 15 is down at 1. Our 15 to 20 is back up to 3. And then our 20 to 25, that's where all of our data was, huh? I got a little. Our 25 to 30 up to 4, or 30 to 35 is at 4, and then our 35 to 40 plus is back at 3. So boom, we have a histogram. So oftentimes when we make histograms, we do have to make these choices, like where should my histogram start? Well, where do you want your histogram to start? How big should my bends be? How big do you want your bends to be? They should be big enough that they make somewhere between usually 8 and 15 bins, or 6 to 15 bins, you know, somewhere in that kind of range number of bins, but that's your choice. Questions about any of that? So again, for our practical applications, frequency tables and histograms will be much more useful for us than stem and leaf plots. But again, stem and leaf plots, they tend to be kind of a step along the way. They're a nice, convenient way to be handed raw data. They're a nice, convenient way to collect raw data. Usually we end up displaying data in other tools if we're going to use it, but not always. I've worked with a couple things where I've been handed data in stem and leaf form. My job was to organize it. And that's fine. As long as we know how to effectively read a stem and leaf plot, we should be in good shape. In your reading in chapter 2, this is all chapter 2 stuff. Your reading in chapter 2, you will talk about dot plots a bit. Dot plots are really just a type of bar graph almost, where instead of having the actual bars, if you've got, say, data that's, goes from 4 to 10, 6, 7, 8, 9, 10. Instead of making a bar at the height, you dots. Say I had 1 4, 2 5s, 2 6s, 3 7s, 6 8s, 3 9s, and 2 10s. The dot plot is like a bar graph made out of dots for each data point. We won't use them a tremendous amount, mostly because they kind of require it to be a small amount of data, because you've got a dot for every data point. If you've got 700 data points, you're going to make a bar graph. You're not going to use little dots. But it is nice because it does kind of conserve the actual data itself. So they're a nice thing to be familiar with. We won't use them too terribly much, but your section does talk about them. Your section also talks a little bit about skew. We'll talk more about skew as we go along into interpreting data and interpreting histograms. So as always, do make sure you're reading through those sections. As always, if you have any questions, please let me know. Is there
Hey,
anything?
Matt.
Yeah.
In the, are you going to record your lessons?
Yes, and I have been recording this one.
Okay.
And I'll post
Just
them.
double checking.
Yeah, and I'll post them like I did before.
Okay.
But it does, for those of you who are new to this, I will make a brick in my Open Math page that has the lecture recordings in them. It does take usually about 45 minutes or so for the computer to reformat the recording. And then I've got to upload it to YouTube, and it takes YouTube a variable amount of time to format it to YouTube. So they're not up immediately. I would love to just be able to go and then post it, but I got to wait for all the stuff to format. But I'll try to make sure those get up in relatively short order. So if you do have to miss a day for whatever reason, that does happen and is fine. You will have access to those. Okay. Anything I can help you with before I let you guys trundle off today?
I have a question about the labs.
Sure.
Should we be working on them now, or should we wait till Thursday?
Really, you can be working on them now if you want to get ahead on them. But really, they're meant to be done Thursday. Okay. But all the homework's open, all the labs are open. So, if you've got stuff going on, especially, or if you're gung-ho and want to kind of get ahead, you're welcome to. So.
All right. Thank you.
Sure. You certainly should be starting to work on the chapter 1 homework and the chapter 2 homework. If you had to kind of choose between should I be working ahead or working on the homework, or should I start working on that lab, the homework first, definitely. Cool. Anything else I can do for anybody? All right. If something comes up, let me know. And I'll see you tomorrow.